editorial boards of Applied Spectroscopy, Journal of Biomedical Optics, and Calcified Tissue International. He's received many honors: Division of Analytical Chemistry Award in Spectrochemical Analysis, Anna Chem Award, the Society for Applied Spectroscopy New York Section Gold Medal and Meggers Award, the Mannheim Award, the Mann Award for Applied Raman Spectroscopy. So we're really excited and pleased to have him here today to talk to us about his wealth of experience in Raman spectroscopy and biochemical analysis. And just on a personal note, it's been a lot of fun to interact with him in the last couple of years on Raman tomography of tissue, and it's a real pleasure to host him here at Dartmouth and hear some of his thoughts on Raman. Please welcome him.
Well, thank you for the kind introduction. I thought I was going to be introduced as the one who was killing off the Jones seminars. I want to talk about several topics today, and since nobody wants to hear me until the middle of the night, I'm just going to leave out bone development, the bone biology, and concentrate on a couple of applications in developing mechanical function. Do I have it on?
Maybe raise it up a little bit.
Yeah, okay. Is that a little clearer now? Okay. There are a couple of applications in bone biomechanics and a couple of applications and cartilage biomechanics and a couple of applications to diagnosis of disease. I don't do all this stuff alone. There are a number of very competent grad students, postdocs, and collaborators who've been part of the operation, and in fact the important part of it. I just want to mention the people whose work I'll mostly be talking about. Current grad students in the group: Kate Dooley, Karen Esmond-White, John David McElderry, and I shouldn't ignore the fact that Mekhala Raghavan is also in biomedical engineering, as is Karen. Matt Shulmerich just left us with his PhD about 3 months ago. So-Ching Chen is no longer here. She's a postdoc at NIH. And I'll be talking about some of her work as well. And I see I've probably left two or three other people who are just as important. Any number of talented postdocs: Jacqueline Cole, a biomedical engineer from Cornell; Frances Esmond-White from McGill University. This is the power spectroscopy power couple. They both won student awards at the same meeting in the same year, FACS meeting. Pei-Shi Zhu's a biophysicist. Kurt Golchuk has just left us for a permanent position. He was a physicist, still is. So was Bill Finney. I'm sorry, Bill was a chemist from Syracuse University. Here's Olivia as a postdoc. She was a grad student with me and did a postdoc as well. Major collaborators, and there are several others I have not mentioned in here, include Dave Cohen in our dental school, materials and biologic sciences, and a couple of his grad students: Steve Goldstein in orthopedic surgery, Ken Kozlov, who was a grad student at the time, is now on the orthopedic surgery faculty, Barb McCready, biomedical engineer, Marianne Misek, formerly of this department, this institution, Blake Ressler in rheumatology, Rams Ramamurthy, who's chemist. I do know some chemists. Lars Stixrud in our geology department. Many people externally, including Mary Tecklenburg, a chemist at Central Michigan. Bob Recker, an endocrinologist at Creighton University Medical School, very major figure in osteoporosis. Dave Feary, a biomechanics guy at UC Davis. Pavel Matusik and Tony Parker, the Rutherford Appleton Lab in the United Kingdom, and of course Brian and Shuba right here. So let's start with a little bit of bone biology. If you're the same way that I am, then you basically had a grade school understanding of bone tissue, that it was, you've all seen the plastic skeletons that appear in classrooms and elsewhere around Halloween time. That's about all that most people know about their skeleton. Except that once in a while, either some part of it broke, more accurately usually cracked, and in an accident, and if that didn't happen to you, you at least knew people who had a broken bone, and then somebody puts plaster of Paris around it, and 4 weeks later, all the trouble disappears. But it's actually a very complex organ. Okay? Here's a cross-section looking at the structure of it. The outer part is called the periosteum. This bone, compact bone, I'll go into osteons in a minute, is part of the cortical bone. If you look in the interior here, and this is most prominent at the ends of the long bones and the vertebrae and a few other places, but not in this section of the long bones, you can see it's a very porous structure with essentially bone marrow in between. It's called cancellous bone, sometimes called trabecular bone, and its function is to be simultaneously strong and light, but it's also fairly easily damaged, and we'll talk about that when we get to osteoporosis. These structures here are called canaliculi. They contain little cells called osteocytes who have a number of functions, including making bone, but also serving as mechanotransducers. They are telling what direction your bone is being loaded in, and are very important in sensing where new bone is needed. They're actually little canals, which is what that means. If you look at this structure, and we'll look at it again, it's circular. In the middle of it are blood vessels, and blood vessels tunnel through these structures and bring new nutrients. It's part of the process of removing old, damaged bone and bringing in, forming new bone, called remodeling. Haversian canals are simply the blood vessels that go through and that ultimately end up being these osteons. If you look at it on a more structural level, I see I didn't bring in put up the hydroxyapatite structure, but you can look at collagen molecules that are decorated with little crystallites of a mineral that is a carbonated version of hydroxyapatite. Not quite hydroxyapatite. That's the hard stuff that you can feel by just tapping anywhere, on almost anywhere on your body. Arranged in very interesting structures, arranged in lamellae for the most part, that is sheets of material about 300 nanometers thick. The collagen molecule, which is the major component of the protein part of bone, or in the jargon, the matrix of the bone, is type 1 collagen, very similar to what's in your skin and in other parts of the body. But it's heavily cross-linked, so it's stiffer than skin collagen. Cross-links both couple the individual collagen strands, and they couple fibrils to fibrils. So the structure is very complex. If you look at the ends of the fibrils, when they're pointing near each other, there's a little gap where mineral deposition starts. And then the minerals eventually cover space between the fibrils, around the fibrils, and give you the hard composition that you know. So here's the collagen molecule. If we look at a long bone, this one's the femur. The middle of that is called the diaphysis. The ends of it are called the epiphyse. And the trabeculus here is what is at the ends of the bone. That will be the part that is most damaged in osteoporosis. The bone marrow, which you may have all seen in chicken bone or in beef or pork or other mammalian food animals, is in the center here. And that's where both red blood cells and ultimately the cells that form and take care of bone are synthesized. The cells that are most important for our discussion are the osteoblasts, the bone-forming cells that lay down new bone material, and the osteoclasts, the bone-resorbing cells, whose function is to remove damaged material. So while your skeleton feels constant to you, in the sense that if you grab hold of your arm today and you do it again tomorrow, it feels exactly the same. Like your skin, where you can see the process, the bone is constantly being damaged and constantly being repaired. So it's really a dynamic living tissue. And you don't realize that because you don't see it every day, and because your impression of the skeleton probably came from the grade school Halloween version of it, and not the scientific or medical version of it. So here's cancellous and cortical bone in more detail. This is looking at one section of the cancellous bone. It is really an arrangement of struts and plates, more or less triangular in their overall geometry, for the same reason that a 19th century bridge looks like that. It's strong and light if it's done that way. If you look at the cortical bone, here are the osteons that I talked about. You can see this circular structure that arises from blood vessels coming up through the center and depositing protein in all directions. So that'll give you a circular symmetry, and then putting over it the mineral phase. So after bone has been repaired, or in the jargon, after it remodels, you end up with it looking like this. Makes very pretty and very dramatic photographs, especially under polarized light. Here's an osteon in detail. We don't need to go over that. Let's look at bone Raman spectroscopy. A Raman spectra is a light scattering spectra. You shine light, laser light, it has to be more or less monochromatic on any kind of material. And you find that a small amount of the light shows up at wavelengths that are a little bit redder than the wavelength that you put on the light. It is red shifted, and the shifts in frequency arise from an interaction with the molecule, which results in a little bit of the photon energy being converted to vibrational energy, ultimately dissipated as heat, and the rest of it reemerging as photons that are at lower energy by the vibrational energy. So the shifts that you see, as you plot them as a function of wave number, frequency of the inverse of wavelength, are all related to well-known vibrations of the molecule. And I put in this greenish color vibrations of phosphate. These are stretches and bends of the oxygens of phosphate relative to the central phosphorus atom. Same thing for carbonate. There's another one out here. More complicated for collagen. That's this pinkish color. And the ones that we're most interested in are stretches of the amide backbone of the protein, and they occur at about 1660 wave numbers. There's a related motion at 1270 wave numbers. We make a lot of use of this great big phosphate, very intense phosphate vibration, and of its neighboring carbonate vibration. Both of them, well, I can do this. You always need a little exercise. Let's see if I can do this right. Okay. Sort of looks like that. Everything going in and out simultaneously. This is the carbon-oxygen stretching motion of the carbonyl. So if I'm an oxygen out here and a carbon backbone up here, it looks like that. Okay. So those will turn out to be the major bands that we look at. This is due to hydroxyproline from the collagen here. We'll talk about these in a little bit of detail. So that's all the spectroscopy that you really need to know. The interesting thing is that the spectra, in addition to giving you composition information, gives you a lot of information on bone tissue quality, the changes in composition, or components of quality related to the age of the tissue, the age of the organism, the exercise it's been subjected to, its diet, mechanical loading, damage, mechanical damage to it, diseases, genetic defects, all of that is in there. Okay? So the information is in the peak positions, where those bands are that we looked at, their relative intensities, their widths, how they behave under polarized light. All of that is important. We look with two instruments, and I've got one here, and it's basically just a modified epifluorescence microscope. So it looks, we generate the spectra inside using microscope optics. And optically, it is essentially an overpriced, high-resolution fluorescence microscope. So we resolve the spectra in the spectrograph over here. We generate them with a laser off over here. We can generate maps and images by putting mechanically driven stages in, conventional XY stages. I don't want to go into all the details of it, but the key thing is that we get light microscopy resolution on anything that will fit on the stage of a microscope. And we get the Raman Spectra with all the good news there. The other thing we use are fiber optics. These are mostly standoff fiber optics, but sometimes impinging on the tissues. So we can look beneath the surface without having to excise tissue. We can look at, and have looked at, living animals, and we will look at living people doing this. Let's take a little look at bone biomechanics. One of the ways of looking at bone is that it's really a mechanical system. It's a structural element, right? I'm not going to collapse into a puddle, and neither are you. And the reason is that our skeletons are maintaining our shape, allowing us to walk around, do all the things that you just do every day. So it's a structural element in the same way that the steel that is and concrete that are holding this building together are structural elements, and it follows many of the same principles, or perhaps the other way around is the way to look at it. And there's been a lot of work in elucidating the mechanics of bone tissue by people who ultimately come from a mechanical engineering background, as some of the people in this audience do. But instead of applying their skills and their theory to bridges, to automobiles, to structures as you normally know them, they're applying them to the skeleton and to other tissues in the body. So we did an experiment that if we had been on our toes, we could have done 50,000 years earlier than we actually did it, which was about 4 or 5 years ago. And that was to make a little indent in bone. And we used an instron, which is a standard mechanical testing experiment, but the cold truth is we actually did the first version of this with the instrument on the left. We took a hammer and a nail, and we made a little indent in bone. Okay, so that then ultimately you do it with an instron. It's a bit easier to control than a hammer and a nail is. But you can do the same experiment, and we did this with bovine bone because it was simple to obtain in large quantities. And with the instron, we could apply known forces to it. And we got indents that varied as a function of force. And then we obtained Raman spectra using a microscope and looking inside the indent, looking right near the edge, and then looking at a control region some distance away. Okay? And then we analyzed the spectroscopic data and the imaging data and saw interesting things. And the interesting things we saw is that if you looked at the it looked different inside the indent. Any place we looked, it looked different than it did when we looked outside. And you can't see it very clearly here, but this is the edge of this nicely calibrated nail. Basically, it's a little cylinder, about 0.5 millimeter in diameter, that is inserted into the instron and creates a circular indentation. So here's the edge of it, and I'll show you an SEM in a moment. And the take-home message is that things look different in the mineral inside the indent than they do at the edge. So the bone mineral, something is happening to the bone mineral when we pound it on this with the hammer, actually the calibrated hammer. And when we look at the matrix, at the collagen spectrum, and it's primarily collagen that you see by the Raman spectra, not the dozen or so other, a couple of dozen other proteins that are present at very low concentrations but are very important both in the development and the function of bone. You see the one that's present at about 90% abundance. And there you see something entirely different, and that is that if you look right at the edges of the indent, the spectrum looks different than it looks in the control region out here, and then it looks inside the indent. In the indent and out where nothing has happened, the collagen component of the spectra look very different. And here's one of the very few hyper details you're going to get. If you look at the amide 1, at this carbonyl stretch, this guy off to the side of the, extending out from the side of the collagen backbone, which is me, then you find out that it has a couple of components corresponding to two different conformations of the collagen, and one of them is more intense right here at the boundary, at the edge. but it's unchanged elsewhere. And if you had been reading the IR literature on bone, you would have known that that's a signature for changes in the cross-link. Absence of mature cross-links, rupture of mature cross-links. So you see signs of mechanical damage in the collagen, but only at the edge and not in the middle. You see signs of changes in the mineral, and we'll get to what they are, everywhere. Okay? So if we look in the scanning electron micrographs, I didn't know how to do this, but Dave Cohn, who's a mechanical engineer, looked at these and says, aha, these are shear bands. This is what you see when you make an indent. You see the results of shearing as these bands at the edges of the indent. So if you bang a nail into anything, you would see this sort of thing right at the edge. And in detail. It's known that bone is much stronger in compression than it is in shear. And so what we are seeing is no change in the collagen, subjected to a pretty huge, pretty large compressive load, large enough to make a permanent indent in it. So the collagen is pretty tough stuff. It doesn't do anything. But the mineral is changing somehow. And we'll show you how. But it's known that the bone does fail in shear, and here you can see the mechanism of the failure, the failure, and that is that you're rupturing these cross links that hold the collagen fibrils together. So you can see that in detail by looking in the simple hammer and nail type experiment, by looking at the Raman spectra. And we've done some more recent work on that where we've been able to see things right before the bone fails, and unfortunately I don't have the slide. We did then looked at this under high pressure. When you're working in the edges of the medical world, it's very useful. I don't know what that is, but it doesn't matter on the right. It's very useful to have a geologist nearby, because the geology people are very interested in the behavior of minerals under very high pressures. They want to know what's going on at the bottom of the sea, inside the mountain, and in other places subjected to extreme pressure. And so they've developed techniques for looking at Raman spectra under high pressure, and that we simply went over to the geology department, to Lars Stixrude's laboratory, and we did this. And the key thing that you can see here, and don't worry about all the details, is that you see systematic shifts in that bone mineral band at about 959, the great big one that you now remember nothing about, except there was a big spike towards the left-hand side of a figure of a Raman spectrum of something or the other. That you see this changing linearly with pressure, and this is hydrostatic compression. This is a closed system, not quite what's going on in bone. But it's known what this sort of thing is due to. With the pressures that we can reach here, several gigapascal, much higher than we were reaching with the instron. What you do in an ionic crystal, like the carbonated apatite of bone, is primarily changing the separation between anions and cations. When you compress, the anions and the cations get closer together. And in fact, in bone, it's known that this occurs in one plane of the crystal, in the so-called AB plane of the crystal. And in the perpendicular plane, the C-axis, there's very little change, if any. Very little distortion of the phosphate ion itself. It maintains the same geometry and none of the carbonate. So this is all known from the mineralogy literature. But of course, people in orthopedic sciences do not read the Journal of Geochemistry and similar journals. So we simply walked over to the mineralogy literature, to the mineralogy people, and worked with them to see what was happening under high pressure. And what's happening then is that we're compressing the crystal. So in the center of the indent where we see changes, we're compressing the crystal, and we very recently confirmed that by solid-state NMR, where we're looking at the phosphorus resonance of phosphate, known in the bone world to be completely useless, because you get no information about the state of the bone from conventional phosphate NMR, but we took a piece of cow bone again, milled it into a cylindrical shape, looked at it in the NMR probe, and what we see, because we weren't able to do this very fast, it was an accident, is that as we compressed the bone more and more, and all we did was make ourselves a little closed container with a screw on the top of it, all made out of ceramics, because you can't do NMR with anything metallic in the system. And we just tightened down with a torque wrench. And as we increase the pressure, you see these little shoulders called spinning side bands that result when you can't spin the thing fast enough. And we found that they increased linearly with pressure. Well, it's known that the intensity of those varies inversely with the cube of the distance between two similar ions, or in other words, with the volume. And it took me a little while to figure out what was going on, because I didn't really know much in solid-state NMR. But what's happening is that you're simply compressing. As you compress the tissue, you're making the phosphates come closer together, and this is independent evidence that that's what's going on. And the cool thing is that the Raman spectra, the NMR spectra, and the properties that you're interested in all vary linearly with volume, or inversely with volume. So you have multiple ways of looking at exactly what happens to the mineral. When you load bone under normal loads, where only elastic deformation occurs, and under abnormal loads where plastic deformation and ultimately failure occurs. And we very recently done an experiment making 2 notches in a piece of bone, bending it in such a way that either one of them might fail, and looking at the state of the other notch, the one that didn't fail, and we find that right at the boundary of the edge of that notch where the stress should be greatest, indeed, from the shift in the Raman spectra, we are very close to the ultimate stress of the bone, and the bone very close to the loading that should make it fail. And that's very exciting because it means we can look at the state of tissue very close to failure. We've also done some work on exercise mice, this under the auspices of the Army. And so this, I don't know where Kurt got this from, but people didn't give it, and he didn't care about the work, really liked this cartoon. So here's our control mouse, and it's eating whatever mice eat in the way of junk food. And here's our exercise mouse. It was being run on a treadmill for 30 minutes a day for about 3 weeks, and then the mouse was sacrificed, and we looked under this conventional loading regime, 4-point bending, at what happened as we fatigued the tissue. And the bottom line is that if you look at the control tissue, if you look at the exercise tissue, the result of exercise, and this is really a simulation of what goes on in military basic training, is that you increase the mineral to matrix ratio. You put on mineral more or less uniformly around the tissue, which means it's probably being generated by osteocytes and not osteoblasts. Cross-linking goes up a tiny little bit, maybe significant, maybe not, but the crosslinks fail in the control tissue and the mouse that's just been sitting around, and they don't fail when when you've been exercised, when you put more mineral under it. The resistance of the bone to damage is greater. If you look at all the little cracks that form, then what you find is that if you fatigue the tissue, if you cycle it back and forth, then the number of cracks goes way, way up in the control mouse, but doesn't go up very much in the mouse that's been exercised. Another indication that exercise is good for you, but what's more to the point is how, if you look at on a finer scale, you see the same pattern. As a result of putting on mineral, every tissue is more able to respond to a high load. So the take-home message is be like that mouse. Okay, so and just some very recent work that we still haven't published looking at correlations between what we can measure in the Raman spectrum and a variety of biomechanical properties. Push the wrong button. And the obvious one is that adding mineral increases the hardness. This is essentially what we found in the exercise tests. And it is easier to see in the older bones because there are a lot of confounding factors having to do with the growth of the animal if you look at younger tissue. Not tremendously surprising that that happens. The plasticity goes down. The fraction of the work that contributes to permanent deformation actually increases if you more heavily mineralize the tissue. So that's in the Raman spectra as well. And if you increase the number of cross-links, then again, this is no surprise, independent of where you are in the age, and you can see 4, 5, and 19 months, you increase the ductility of the material. You make it more flexible. So by looking at the Raman spectra, intrinsic to it, inherent in it, is a lot of information about the state of the tissue, about its mechanical competence. And that's very useful because you can at least envision the Army somewhere in the middle of basic training, putting a Raman fiber probe on everybody's shin and looking to see whether they are responding well in the sense of becoming more resistant to fracture than the new recruits. Because one of the problems that the military services have is that they lose a large fraction of recruits during basic training, essentially to fractures. So knowing either in advance, if possible, but certainly partway through the process, that you've got somebody who's going to be more susceptible to fracture, less susceptible to fracture, which you can't tell from the incoming physical, is very useful and very valuable information. Okay, so let's talk about osteoporosis, about non-invasive Raman spectroscopy, because this is a very interesting topic. One of the problems, or one of the needs in medicine in general, is for diagnostics that are non-invasive. All of the people in medical practice know, and I heard an uproariously funny seminar by the late Pierre Delmas, who unfortunately died in his middle 50s, about compliance issues in endocrinology. When somebody goes to the doctor, which happens only in a fraction of people who ought to be going to the doctor then sends them somewhere for a test, and then only a fraction of those go. And so the problem is getting tests that can be done non-invasively, and the conventional ones for osteoporosis, completely non-invasive. It's an X-ray test. We'll get to that and what's wrong with it in a few minutes. It isn't like a colonoscopy that people will fear. It isn't even like a blood test where they jam a needle into your arm and draw a little bit of blood from a vein. You just have to lie there for a little while a machine passes an X-ray beam over you. And unfortunately, you have to take off your clothes, and you can see that's an irritation. But it doesn't hurt. It doesn't even hurt as much as having a needle in your elbow for a blood test. But nonetheless, many people who are given a script for going to a radiology clinic, getting a bone X-ray scan done, simply never show up, and they find all sorts of reasons. Oh, I'm too busy to do this, I'm afraid it will hurt. All of the reasons you have for not going to the dentist with the same kind of outcome. Okay, so a little bit about osteoporosis and what it is, something that everybody has heard of. And what it really means is thinning of the bones, and it occurs systemically, but the biggest problem is in the cancellous bone, in this porous, okay, we'll get to that. In this porous bone right here. Normal bone looks more or less like this. You can see the somewhat triangular structure, ideally triangular in here, but you can see it's an open work, it's a lattice work. Now osteoporotic bone looks like that, and you can see here's a region that's almost completely eaten through. it looks as if somebody had thrown a bottle of acid on this cancellous bone, because that's essentially what happens. Okay? And you can see very clearly in the scanning electron micrograph what is going on. So here's the section of the femur, and the damage is actually going to be done either here in the femoral neck or here in the trochanter. That's where the so-called fractures occur. So it's a serious disease. Americans currently suffering from osteoporosis, and about 3/4 of the cases are from women and about 1/4 for men. Although the mechanism applies equally to men and women, it strikes women about 20 years earlier than it strikes men, which means that in some cases the men are going to be dead of something else before they suffer serious osteoporosis. Well, I have bad news for you folks. We're all headed in the same direction, but let's enjoy the journey. About 75% of the cases are women, because osteoporosis starts to set in soon after menopause. Okay, so somewhere in the early 50s. In men, it occurs about 20 years later, which means that serious damage is likely to occur in women while they are still in otherwise good health and still around, whereas in men, in some cases you can see it, but in other cases, by the time it is far enough advanced to cause damage, would have been far enough advanced, they're dead anyway. Okay. It's a big medical problem. The hospitalization is 19 billion per year. This is the newest data that's out there, 4 years old at this point. It's a little bit more now, but the take-home message is a lot of cash is expended on this, a lot of problems for the people who are being hospitalized, obviously. About 19 billion a year, maybe 20 or more now. And it results from an imbalance in osteoclasts, which are those cells that resorb damaged bone that we talk about, and osteoblasts, that are the bone-forming cells. Osteoclasts operate by sealing themselves to the surface of damaged bone, and have an internal pH of about 4, which is enough to dissolve a phosphate. And I'm a chemist and I know these things. So it really is throwing acid at the bone. So that's fine. So you dissolve away the mineral in this acidic environment, and then you hydrolyze proteins, and then the damaged tissue is gone. And that's supposed to be followed by osteoblasts, which come along with a very complicated sequence of events and lay down new material, resulting in those osteons that we showed you. But the problem is that this process is limited to the sex, is linked to the sex hormones. And so as they decline with age, relatively abruptly with women at menopause, and more slowly with men at older ages, osteoclast production continues more or less unabated, but osteoblast production slows down, so you can see what's going to happen. You go on merrily removing damaged bone, but nothing is coming in its place. And eventually you end up with that. Okay? And then any tissue that looks like that is easily damaged. It's easily broken by so-called low-energy fractures, also called osteoporotic fractures, falls of one sort or another that would normally not damage the bone. Okay? So those are the low-energy fractures. So there are several sites that are very common. Okay? One of them is the upper spine, the thoracic vertebrae. And this is your back out here. This is the chest cavity over here. You can easily visualize why it fails towards the chest cavity. That's the side that's heavily loaded. All the weight of your skeleton, all the internal organs in the chest are being carried by these thoracic vertebrae, and as they begin to be eroded, or as they become eroded, the tissue simply fails in that direction, and that gives rise to the stooped over behavior that is stereotypical of old age. And you've all seen people who are stooped over like that, often very badly deformed. And the only way to fix that currently is basically to pump in an acrylic. pump in plastic into that and try to straighten the bone. So the better way to do things is to try and prevent that from happening or minimizing it in the first place. So the major and most devastating site is probably the hip, really meaning the thigh bone, okay? And the failure is typically here at the femoral neck, or in this line right around here, between the greater and the lesser trochanter. Okay, so there's those things where there's trabecular bone, cancellous bone on the inside. These are the things that fail. Typically when you take a fall that you or I wouldn't notice. Maybe there's a loose rug in your house and you trip on it. Maybe you stumble on something and you take a fall. And if it's a sideways fall, you will land on the hip. And then in some cases that results in a fracture, and it's devastating. Because associated with the fracture, not only is there the inability to walk, and unless something is done, and something means hip replacement, you'll never walk again. It's also subject to infection, and that can result in death. And the strain that's put on your body may make other conditions that you have just generally worse. So excess mortality associated with hip fractures. So when you hear of somebody dying of a hip fracture, you wonder, why would somebody die of a broken bone? I went skiing, I broke a bone, and here I am. That's the reason why. We're talking about a very serious fracture, something that can't be repaired by putting a cast on it and letting time go by, and something that increases the stresses on the body enough that if you aren't getting serious further damage to the tissue itself, other things can often kill. The third major fracture site is the distal radius. That's the bump above your thumb that you can feel if you just stick your hands there. And that fracture occurs if you take a fall and try to break the fall by doing that. Okay? Falling over and putting your hands out, then you put a huge load on the distal radius. The cancellous bone fails. That's called a Colles fracture in the jargon, and depending upon which subcategory of it, there may be somebody else's name associated with it. But that's the so-called wrist fracture. So these are the major sites. There are other sites of osteoporotic fractures as well, but these are the biggies. Okay? So the diagnosis is done by a low-energy X-ray technique. That's called DEXA. It's currently the gold standard, and what it really means is how much is an X-ray beam at the appropriate wavelength attenuated by calcium. The calcium density, as it's called, with a second wavelength for background correction, because other things than calcium are absorbing. And so DEXA stands for dual wavelength X-ray absorption, sometimes abbreviated DEXA. It's the current standard. There are all sorts of problems with it. I'll get a couple of them. Diagnosis of osteoporosis is a T-score of lower than minus 2.5. So what a T-score means is a measurement of calcium density, sometimes called areal, meaning of area, a certain number of standard deviations below the mean of a reference population of young, mature, healthy women. Okay? So assuming that the reference population is appropriate, and it varies by ethnicity, the T-score is how many standard deviations is your bone density measurement below the average for this reference population. And that's usually specified at the hip, although it's also measured at the distal radius and at the lumbar vertebrae, the lower one, simply because you would otherwise be going through the entire chest cavity and picking up the ribs. So that's the diagnosis, and there are a lot of problems with it. Aside, some of the ones you can immediately figure out, and that is you're making measurements on somebody's body, comparing them to tens of thousands of measurements made on other people, and how do you know that everybody is in exactly the same position, measurements being exactly the same place? And the answer to that is no, you don't. The problem has got very poor fracture risk because it misses a lot of things. A lot of factors are not captured by this technique. And it is especially bad in follow-up for patients on anti-resorption therapy, on the very popular drugs, the bisphosphonates. They're analogs of hypophosphate. We don't want to go into the chemistry of that, but these are sold under the trade names like alendronate and Actonel. Those are the two trade names. I'm sorry, Fosamax and Actonel. They're trade names for alendronate and risedronate. And since Fosamax just went off patent, it's now called alendronate. Okay, so the reason it doesn't work is it doesn't measure anything about the architecture of the bone. So all those structures that you saw, the thickness of everything, that's all missing. Doesn't measure anything on composition and the things that are related to that. And when you lump all these things together, total amount of material that's there, the architecture, the composition, those go into a vaguely defined measure called bone quality. Okay? So you're missing a lot of these quality components, and as a result, people with a T-score that is better than minus 2.5, who are called osteopenic if they're below the mean, and fracture. And people whose T-score is much lower than minus 2.5 sometimes never fracture at all, and that's even after you factor in the other risk factors, what kind of lifestyle are they living, that sort of thing. You still can't get too much out of it. Maybe, depending upon whom you read, fracture risk associated with the bone itself, maybe 2/3 of it at most is captured by the T-score. It's even worse when you try to predict fracture risk, because small changes in bone density often result in big changes in bone performance, and the opposite is all true. Also true, it depends on where the new bone happens to be happens to be deposited. So there's an emerging consensus that DEXA ought to be replaced or supplemented, and there's a good reason for that. It doesn't work well. And there's a bad reason for that. And that is that the pharmaceutical companies want something new to help them to sell the next generation of osteoporosis drugs. And if you know the history of it, there's a very strong linkage between the spread of DEXA and the spread of bisphosphonates. And it's not clear to me still whether bisphosphonates are popular because DEXA was taking off, or because DEXA was taking off because a couple of companies were subsidizing the use of. And then there's a realistic reason for why people want to replace DEXA, and that is that Medicare reimbursement is dropping from $100 per DEXA measurement per session to $45, at which point the people who are practicing DEXA are going to lose money, or at best not make any money on it. So for a variety of reasons that are good and bad, DEXA, people are looking for a substitute for DEXA, and there are candidates for that. One of them is quantitative tomography, X-ray tomography in a couple of versions. Another one is magnetic resonance imaging. Ultrasound, easy to do, very inexpensive, but dicey. And we think maybe Raman Spectroscopy has a shot at this. I'm running out of time, so I'll speed up a little bit. So we've shown that there's information about the state of the tissue, independent of DEXA, in the Raman spectrum. And here it is. Carbonate to phosphate, mineral to matrix ratio are correlated with this. And this was done on tissue where we'd matched on autopsies and hip replacement tissue where we'd matched all the familiar parameters, and we still find there's information that isn't captured. Okay? We're just starting a multi-lab, multinational study using Raman spectroscopy, FTIR, quantitative CT, and a couple of other techniques under the leadership of Bob Recker at Creighton University, looking for what are the best predictors of fracture susceptibility, and we'll get our first biopsy specimens in November or December. Looks like December. So if you try to look at diagnostics. What's going on beneath the skin? You want to do things non-invasively. Here's the conventional picture, a little more sophisticated than grade school, but the idea is the same, that you view the skeleton in isolation, the way you saw skeletons in grade school. And it looks like that. Okay, here's a Colles fracture, distal radius fracture here. The reality is that it looks like that under the skin. A lot of tendons covering the region that you're interested in, and then there's an overlayer of ligaments and an overlayer of skin. So you've got to go through all that very dense tissue before you get to the bone. It scatters light badly. Its collagen is type 1 collagen, looks like almost like what you're looking for. So a measurement through the skin that looks trivial if you look at this turns out to be quite complicated because they all scatter light. Okay, tissue optics, this is well known. Multiple scattering, that's a big issue, and certainly in an institution with Brian Pogue in residence, there's an awful lot that is known, an awful lot of elegant work done on light scattering. So you've all seen this, even if you're not in the optics component of the program. You've all done this experiment where you put a laser pointer up against your thumb or some other finger, and you see the light coming out every place on the other side. That's the multiple scattering. And there are two general approaches to looking beneath the skin in the presence of light scattering. One of them is a time-resolved measurement, maximize the collection from light coming right back at you from the desired depth. And another one is to spatially separate the excitation and collection points where you put light in, where you take light out, usually with some kind of fiber optic system to define the separation geometry. And that's the approach that we've used. In the Raman world, it's generally called spatially offset Raman spectroscopy and was introduced by Pavel Matusik and collaborators about 3 years ago in a widely known paper in applied spectroscopy, and that was done with layered powders, and I don't have time to go into that. We showed a year later that you could do imaging using this very crude and not particularly useful version of the two-dimensional component of tomography. And we've since abandoned this configuration, which isn't particularly good, but was easy for us to use with others. And we've looked at live specimens, dead specimens, excised limbs. These are cadaveric tissue from a human male, and our very first results weren't all that bad. We were looking at tissue about 3 millimeters below the skin with that configuration we had before, and we could actually find something that approximated the Raman signal. So it worked almost on the very first try, and we were able to validate the measurements by removing overlying tissue. Okay? So we quickly moved to more sophisticated approaches to that. And we find, not very surprisingly, that the spacing governs where you're going to retrieve the signal from, and that the optimum space, there is an optimum spacing at any depth. And we worked out techniques to easily figure out how to decide what the optimum spacing ought to be. We can get very good ratios, very good measurements of the carbonate to phosphate ratio with less than 1% error, and worse in the area largely because it is difficult to do an accurate background subtraction. That affects area more than height, as it turns out. But we can only go a few millimeters down. Okay, so we can reach the cortical shell of the distal radius, but not necessarily the cancellous bone. So we've actually worked both with excised tissue and with live animals. So for excised limbs, very simple protocols. Just remove the hair with a depilatory, because that's easy to burn. Moisten if necessary. And with exposed tissue, you just remove the soft tissue. With a scalpel, that's all you really need to do. And here are a couple of people working on that. And for live animals, you obviously have to anesthetize them. Most mice are not particularly cooperative. and restrain them. And so here you see a mouse breathing into an anesthesia system. The Raman fiber probe is up in the air over here. A little hard to see the mouse, but its nose is in the anesthesia cone here. It's being taped down with a little bit of tape, and it's on this platform that's essentially a mouse hospital bed. We can twist it this way and that. Okay. So it actually works well. We've looked at a variety of strains of mice, and the errors seem to be correlated with density of hair follicles, because hair burns more easily than, because it's very highly pigmented, than the skin, and we actually do fairly well. And if we look at the average over a lot of measurements, you can see that we get very, very good results, very, very good comparisons by height between the exposed bone and the through the skin measurements made on alive mice. So good. The working with Brian, whom I called up out of the blue and asked if he would like to get involved, and we've now done diffuse tomography. We'd read Brian's papers and those of the other people in the field, so we knew vaguely how to do this. So we set up a collaboration to do it, and I certainly cannot tell you nearly as much about this as Brian can. But basically, you inject light into the system, you gather the Raman spectra, you do this through a variety of angles, and then you reconstruct a 3D image of the target using software that was developed by Brian and Shuba right here. So we actually did this on a dog leg, an X-sized dog leg, so we had this on a stage and we could go round and round. And we illuminated on one side, and then we collected everything on the other side, and that's an easy configuration to criticize. The key thing is we were actually able to do a pretty reasonable reconstruction. So that's going to sit, that has been submitted to NIH. Study section meets on the 2nd and 3rd of February. So you can be sure that all of us will be holding our breath from now until the 2nd or 3rd of February. And the technique works very well. We hope that study section thinks the same. We're now developing more elaborate configurations. It's just a mock-up, and doing modeling with phantoms that are very realistic. I don't have time to talk about this. I have only a couple of minutes to talk about osteoarthritis, which is another major problem. About 27 million Americans have this. This is degeneration of the joints. Most typically, the knee and the hip are the ones that are affected. And with an aging population and increased obesity, which just puts more mechanical strain on the, you get a lot of osteoarthritis. You get about 80% of people who see a doctor with some kind of limited function. They're having trouble walking, basically. Economically, about $12.7 billion per year expended on medical intervention. And nobody treats it, hardly anybody treats it in the stage where you can do something early on. Partly because most of the people who do this never actually go to a doctor when there might be a chance in which to catch this before it proceeds to the point beyond which you can't do anything. Okay? And there isn't any way to, one reason is there's no way to do this. So we're now in the midst of trying to develop ways that are minimally invasive. If you look at, whoops, the knee joint, here it is. What we are doing is looking at fluid in here called the synovial fluid. It's a very viscous material. It's part of the cushioning system of cartilage. And the cartilage itself is degraded by mechanical action. It just gradually wears down as you age. It can be damaged by severe impact. And the damage shows up in the synovial fluid as fragments of collagen, of hyaluronic acid, the gooey stuff, calcium phosphate crystals, and some enzymes. So this is what you want to look at. Here's normal cartilage. You can see the problem right here with a damaged knee. The bones are grinding against each other. It hurts. The conventional measure is the so-called Kellgren-Lawrence score, basically measurement of this gap at defined positions. So we've looked at the Raman spectrum. The key take-home message to you is that there are signatures of early stages of osteoarthritis in the Raman spectrum of the synovial fluid, and we do this measurement by simply making a draw of synovial fluid from the knee, a conventional and not very painful procedure that orthopedic specialists and rheumatologists are quite familiar with, then depositing it, a drop of it, after some pre-treatment, and we get a ring of the proteins and hyaluronic acid around the outside, and we look at the Raman spectra. And the take-home message is that if you look at the difference, in particular, here's the key one, between undamaged tissue and damaged tissue, there's information about that in the Raman spectra. That's cool. That means that you can do something that doesn't hurt. And remember, I told you that things that don't hurt are more likely to succeed. People will accept them. Even with a poor compliance rate, some people at least will go in. Doctors can prescribe training to minimize the damage to the joints. There's some promising possible therapies in the wings. But the key thing is that you got a chance of intervening if you catch this thing early. If you're out here, forget it. There's nothing to do but give people painkillers and to replace their knees. So we're there. I don't want to go into all the details of that, but I do want to acknowledge again all the people who are really doing this. This is the current group. I'm the trained SEAL over here who claps his hands and tries to make money come into them. But these are the people who really do the work and who I'm really proud and delighted to be associated with. Thank you.
But if there's some questions, now's a good time for them.
Tried to keep it close. Okay.
One up here.
Thanks very much. There have been some individuals who speculated that the cartilage damage is secondary to bone densification.
Yeah, that's true. The current view is that that arthritis is really a disease of the entire joint rather than just of the fluid, but it's also the case that you do get the damage showing up in the cartilage and in the synovial fluid. It's much easier. We have coupled a Raman spectrometer to an arthroscope, to the gadget that clinicians use to look at the state of the joint, but it's much easier to see what's going on in the synovial fluid because you just put a big needle in and draw a milliliter or so, and that is much easier. You don't have to give a patient a local anesthetic and jab a very big stick into their knee. So it's better to look at the synovial fluid as a practical matter. Please.
What was the age and sex of the mice that you studied by looked at after exercise?
They were male mice at the equivalent of young maturity, about 2 or 3 months, about 3 months old. I don't remember the exact age. They were C57 Black 6, which is the standard strain.
Would the difference be greater if you're on female mice or older mice?
Well, the answer is yes. We would expect sexual dimorphism. Women do not put on bone mass at the same rate as men do under equivalent exercise regimes. The exact reason, I mean, you just ask bone biologists and they'll say it's hormonal, meaning we don't know what, but it's different in men and women. The answer is there, you would expect that, but the Army was calling for a particular set of proposals, and they wanted it done on males rather than females. But yeah, the follow-up study, doing the same kind of thing on female mice would be very interesting. And then, of course, development of this into a practical examination technique obviously would be very, very interesting. Because it is, as I said, a big problem. Okay.
Seems like you've made progress on getting Raman, in vivo Raman, for the wrist.
We're trying.
For the wrist, for the radius, but looks like the distances are a little large in the hip and the...
Right. We can't get to the... Pardon? Yes, there is a correlation. Right. Lots of arguments about the extent to which damage is systemic and to which it's focal. But all of these are tissues that are loaded. under normal conditions, and so they will be where you would expect the most remodeling and the most repair to go on. So if you've got problems in the distal radius, you would likely suspect there will also be problems in the hip, and that's generally true. And in the vertebrae, you often see them early because there the signs of compression fractures are pretty obvious. Even to people with no medical training, you see the characteristic stoop posture. So that shows up even if somebody never goes to a doctor. But yeah, you would expect to see them at any of these, see similar problems at any site with an outcome that depends, in part at least, upon what kind of environment the patient lives in and what the patient does. Okay, and that's something over which doctor has no control. Please.
I'm not sure exactly how to say this, but how does the tissue compare to live tissue?
By dead, do you mean necrotic, or by dead, do you mean sacrificed? Okay. Question is, how does dead and live tissue mean? And yeah. The answer is it's pretty close. It depends upon what you've done to the tissue. So we try to use only fresh tissue in the jargon. If you fix the tissue with glutaraldehyde, then you're cross-linking the collagen everywhere. With some of the procedures, you can actually extract some of the mineral. So we try to work with fresh tissue. And if we have to store it, we flash freeze it and store it at -80, which is not completely non-damaging, but does minimal damage to the bone. So obviously not everything can be done with fresh tissue, and certainly if you're looking at human subjects, you're either talking about biopsies, which can only be done, or only usually done at the hip, at the iliac crest, and we're not in the human sacrifice business. So the only thing that can be ethically done is to look at biopsies that are part of some medical intervention or some approved study. So relatively rare, which means that with humans you're mostly going to be looking at anatomical donations and tissue that has been removed, say for a hip replacement. Okay, and you do the best you can. Okay.
Well, Michael, on behalf of the engineering school in Dartmouth, thank you very much.